So I borrowed this from first Chinese medical text of 2600 BC, and I think that would probably resonate very well with all of your physicians who are sitting in this lab. The superior doctor, I think I'm going to actually stand here if you don't mind, so that prevents the disease. A mediocre doctor treats the disease before evident, and an inferior doctor treat the full-blown disease. When I saw that, came across this, I thought that's a tremendous statement, and so consequently, I know that all of us in this room are obviously looking at the very first bullet, and that's why we are continuing our professional life to be indeed a preventative clinician. To prevent, we obviously have to know the cause. If we don't know the cause, we're just throwing really dark and completely dark with probably a blindfold on, if you will. And genomic remains to be the most accurate tool when it comes to identifying a cause of a disease. And certainly environment, though it plays a significant role, it remains still to be the effect and not necessarily the cause. However, it's mind-boggling how many genetic tests are out there and how many are added. And so as a clinician, as has already been brought up, you scratch your head and you say, well, which one am I choosing and why am I choosing? This is from a CDC report, and it basically shows the evolution of genetic tests to 2013. We have over 2,000 tests, and now, of course, is even higher than this. And the last that I know, they're looking at about an average of genetic tests being added to the pile, if you will, on a daily basis. So that's a significant number of discoveries. And of course, as Dr. Corey mentioned, since 2003, when the entire human genome was was opened up, more and more discoveries happen. And of course, amongst those, there are some that are less honorable, which we are all aware. But for the good part of genomic, medical genomic, it really is something to be very proud of. So the genetic tests basically examine the genetic codes that are inside a cell of our body, regardless of what the source of the cell is. It could be a drop of saliva, it could be a cheek swab, it could be a smear of blood from our fingertip, or it could be just a strand of hair or a whole tube of blood. Regardless of where you get the cell source, the DNA is going to be the same across the board. The genetic code that was explained so elegantly by Dr. Corey is going to be remaining the same. All of us, at some point of our life, regardless of whether we believe in genomic or not, are going to need a DNA testing done at some point of our lives. Whether it's to decipher some genetic disorders or an inherited health condition. If you're interested in our health and want to just simply do a health screening, if you are going to need a transplantation or a blood transfusion, if we need to find out a kinship, paternity, maternity, or siblinghood. If we are interested in understanding our genealogy or ancestry testing, if we are at a third state of our disease that will require some sort of gene therapy, even for forensic testing, heaven forbid, at some point of time, it's possible that we get implicated in that, or even for dating, believe it or not, there are certain genomic testing. In fact, the HLA testing has been known for centuries in animal kingdom to be very closely linked particularly has been very beautifully shown and demonstrated in cheetah population, that they actually, the HLA testing is used for cheetahs to find their mate based on, anyway, so, and now I know that there are dating services that actually have begun to use HLA typing in order to recommend the best mate, if you will, for us. Anyway, so genetic testing is nothing foreign, is what I'm trying to say. At some point in time, all of us will come across using it. But in general, there are reasons for genetic testing, and this table categorizes it somewhat. It definitely can be used to confirm a diagnosis. That's given. It could be predictive, which a lot of us and every good clinician would want to certainly tap into that power of genetic mutation and its association with potential disorders that may be happening down the road in our lives. The other reason that people use genetic testing or genetic testing is used for is to understand the family history. Is there a genetic recessive disorder potentially that we are not aware of, that we have been so fortunate that it's been, a dominant copy has covered and we are not, but then it could be potentially hidden in us and we could be passing it down to our offspring. A prenatal, everybody uses that, especially in the day and age that the onset of pregnancy is now going to be somewhat the average age being 30 plus anymore in the most advanced countries. Women don't get pregnant when they're only 18 years old anymore. And so consequently, the risk of having a child with mental or physical disability can be certainly tested, or mental disability is something that we certainly see used periodically. The newborn screening has been there for decades and decades. That is a necessity that they do a hill stick and once the baby is born for using the preventative health measures. PKU that I brought up as an example is something that's familiar to everyone. Other genetic, of course, the forensic testing, being and identifying at a criminal scene, or being a situation where there is like a catastrophe, a natural catastrophe, a disaster, or being a terrorism, you name it, that's something that can be certainly used for legal purposes. And of course, research has been, all along something that geneticists have been using this as a discovery tool, if you will. The genetic testing is probably the most prime discovery tool. Something is missing here, but that's okay. There are limitations, certainly, in there are limitations in genetic testing, and the biggest limitation is that we provide information that could be misleading and potentially harmful, either physically or psychologically, to recipients of that genetic test. And this is from the 23andMe disclaimer that is apparently on the report, that basically for the raw data, it's announcing that this is an advanced view of an uninterpreted raw genomic data, which includes data that has not necessarily gone under complete scrutiny. It has undergone a general quality review. However, only a subset of these markers have been individually validated for accuracy. As such, the data from 23andMe's raw data feature is suitable only for research, educational, and informational use, and not necessarily for medical and diagnostic purposes. So people should be, there's nothing wrong with utilization of 23andMe. There's nothing wrong with the accuracy of their testing. However, it is imperative for people who just say, oh, it's a cheap test, I'm going to spend only $99 and just know my entire genome. First of all, that's a misconception. They're not going to go their entire genome for reasons that we will see very quickly what the entire genome testing is about. For second, a lot of the information there is not diagnostic at all, not for the purpose of diagnosis, and so consequently to just spend $99 and expect that, I'm just going to know exactly everything about my genomic is a misconception. And so the other limitation that the genetic testing has is that, when you do a health screen and a healthy individual, or what appears to be a healthy individual, which all of us are very curious about our gene, is that the result doesn't necessarily always mean that if you have a given gene or mutation, there necessarily doesn't mean that you're going to develop that condition, and vice versa. When a negative result is obtained, that doesn't guarantee that you're not going to have the problem or the certain disorder at any part of our life. There are many other factors that also play a role, and many other genes that may not have been tested, despite the fact that you think you've been tested. So what are some of the types of genetic testing? And I think that I have chosen this for the mere purpose of the misconception that is out there, the confusion that is out there. What genetic testing what is a genetic testing, for God's sakes? Is it my entire genome? Or is it that one SNP? And in what way? Why do I want to pay $90 for one SNP when I can pay $99 for my whole gene? Isn't that what at times you ask yourself? I'm hoping that this will shed some light as why, because it's not entirely accurate what we are hearing out there. There is no single genetic test that can potentially detect all the genetic conditions. That's just right off the bat. Beyond the shadow of doubt, I give you my words, and this can be going on for many, many years. At least we are not in the Gattaca world yet. And for those of you who may have seen this movie, it's grand that when you are born, you can be putting together some best ideal genes to create Mrs. and Mr. Perfect of the future. It hasn't happened yet. It's probably going to happen someday, but I don't know when that will be. So there are types of genetic testing that those that will actually involve some DNA sequences at a fine-tuning level. Those would be either single gene testing, a panel of genes, a large panel of genes, or scale of genes that will be either our entire exome or the whole gene, for God's sakes, right? Not the $99 deal, guys. And there are others that will be on the chromosomal analysis and a gene expression, as so beautifully described before this by Dr. Corey. So we're going to take a look at all of them, and I'm going to start with the easier one that are more familiar to you as a clinician. That because it goes back to so we weren't even born. Starting with the chromosomal testing. So I'm not going to go through this because it was beautifully explained by Dr. Corey. The genetic material essentially is, as she said, if you were going to unwrap that spaghetti analogy that she used, it will be about 2 meters. I'm 1 meter and 64 centimeters. I am shortening as I'm aging, but so you can appreciate that. But by 2 meter long is the expansion of it. So if it is, they are structured, as she mentioned, they're wrapped around histone proteins. And so structurally speaking, they come in 23 pairs, one from each parent. So that's the chromosome. We have always in biology books seen it, and that's precisely what it looks like when you do karyotyping, right? So the chromosomal changes could be a lot of variability. There could be a deletion when a portion of the gene is entirely, or a chromosome. Chromosome and genes are interchangeable, obviously. It's just nothing but a whole bunch of genes wrapped around a whole bunch of histone is what collectively is referred to as chromosome. So, it could be a translocation. Often we see this in cancer, in hematologic cancers, when a piece of gene or chromosome breaks off and lands on another one, and it initiates a lot of mitotic division. Or it might be inversion, which we see this often in evolution, when a section of gene is snipped off and it just inserts backward, and it totally calls for something differently. So consequently, we have evolved over time, right? The foundation of evolution really comes from most of these. There's nothing really exotic about it. A lot of these chromosomal abnormalities to this date are karyotyping of fish, the fluorescent in situ hybridization or so on a macro level are utilized. And they are really probably better, and because often even the whole genome sequencing is not going to be indicative of this, not very easily at least, so that they remain the method of choice. So this is for those of you who have worked and seen a karyotype, that's precisely chromosome number 1 all the way to a Y or X chromosome are what they're going to look like. So you know a substantial utilization of chromosomal karyotyping is determining, when they use amniocentesis and they spread it out and slap it on spreading it over a karyotype. Do I have 3 copies of chromosome number 21 to indicate the presence of Down syndrome per se, right? So this is something. So that's genetic testing. We all have known that, and there is no confusion about it, right? So the examples of this, the Down syndrome, the Cry-Du-Chat, when there is a chromosome number 5 piece is completely missing, it would be much easier to look at that at this chromosome number 5, and these are being normal. But if this piece is missing, the head is missing, Cry-Du-Chat, non-negotiable, and nobody questions that. Or if you have sex chromosomal abnormalities, Turner syndrome, when there is one X chromosome missing, you expect to see, well, this is a boy, we have a Y and an X, but an X and a Y. But if this was a girl, it would be 2 X's, obviously. So if this was a Turner syndrome, we would basically have just the one X chromosome, non-negotiable, right? We've never questioned genetic testings before, have we? We've never had any problem. So why, despite the fact that we have so much information now, why are we so confused, right? That's why we have this discussion today. So, or Klinefelters, when we have X, Y, Y, X, Y. Anyway, then we go to the gene expression. Dr. Corey already got into the epigenomics and the gene expression. Well, everybody loves, for most part, loves cat. Everybody uses cat example. Well, here is the prime, beautiful, calico cat was used as a gene expression. Well, this was in an X inactivation that she used calico cat. Well, I didn't know she used the cat example. I would have used a dog one. But for those of you who are cat lovers, Siamese cats, this is a beautiful, exemplifies the pattern of gene expression that basically you look at the set of genes, they're all the same, whether it's in your saliva or in your toe or your liver or in your blood. But the way that we phenotypically show ourselves is that, granted that the set of genes are there, but they're going to be, as she explained it, they're going to be turned off. This cat it's got a pigment gene that are going to be more predominantly expressed in the colder areas of the body, and hence it explains the extremities being so dark, right? So the gene expression is very diverse. It's controlled. It's got a controlled pattern. And in the world of evolution, there has been a reason for some of these genes in a calico cat. And it goes back to where calico cats come from, why they have had to have a protective mechanism against probably the sun rays up above versus the rest of their bodies, and so forth and so on. Or who knows what has happened to the cat's evolution to get to this point of time. But regardless, what's important to understand is, for those of you who are very smitten by epigenomics or expression, please understand that is a very complex method, and I will express this a bit further, that when you're looking at a given cell, it will be playing violin, whereas the next cell could be playing guitar, based on this, the guitar gene is off or on, or the violin gene in the neighboring is off or on, and also the given time. The circadian rhythm that you experience in your hormonal balance, that's your off and on button, man. But otherwise, the genes are there. They're not going to go through sleep and wake up. They're going to be turned off and on depending on the time of the day. So it's very temporal. Genes are. This was already beautifully expressed. I'm not going to go down this path. Just so this is a nucleic acid, and here is your mRNA, that is, or the RNA strand that's being duplicated, is photocopied, and that's the whole idea behind transcription. And as mentioned earlier, that's just transcribed. This photocopy is going to exit the nucleus and land on ribosomes and other machineries of your cell and translate to protein to be the Siamese cat brown ears, right? So the gene expression is under control of many things: the activation or deactivation of the chromosome, when the transcription starts, when the transcription ends, processing of RNA. So the RNA processing, just very briefly, as was mentioned earlier, yes, this photocopy is made, but that's a nascent RNA. It's not going to have, it's too large. It's 2 meters long, folks. It's not going to be creating a codon, a protein or a triple nucleotide necessarily. So it's going to have to be spliced out. Parts of it is probably going to be having no information. What parts are going to be spliced out is going to be determining the expression of your gene. What are some of the translocation of them? Dr. Corey mentioned those tRNAs, when they're going to be just moving things around. Which set of them are going to be turned on? Which set of them are going to be moving in and out of the cell? Which part of the mRNA is going to be degraded? And what are some of the post-translational, even after your protein is born? Still, you have a post-translation modification that's going to be happening before we are going to see the bottom line. So gene expression, we may be salivating over, folks, but they're not going to necessarily have that. I can't tell you, here is your SNP, man. You're potentially going to be, have a predisposition to color blindness. Well, I'm not, however, going to be able to necessarily tell you, unless if I'm going to take a piece of your eye out, I'm going to tell you, yes, your gene is going to be expressed or not. Okay, but the environmental factors that was previously discussed also are going to be obviously significantly playing a role in altering all of these factors that we just talked about. That are going to be involved in transcription and translation processes. So this is really cool for those of us who are into health. The nutrients could potentially, Dr. Corey mentioned the transcription factors that are specific. But it's interesting that you can have a crosstalk and a crossover of a food particle could be acting as a gene transcription and turn something on for you. An example of it, for those of us who love fat, there is a hepatic lipase gene that could be associated with an increased protective HDL. Well, go to town and have as much high-fat diet as you can, if you're indeed blessed enough to have that hepatic lipase mutation. Now, doctor, is it a wild type? I dare to say that's a wild type, right? Because most of us are not so fortunate. So and then as such, there are other genetic variations that could be altering the expression of functionality of genes, particularly when it comes to food. Majority of us here are trying to give people direction to a better life, to improving, to a protective. So something as known as PKU, stay away from phenylalanine. And we know that you can use a sweetener and has phenylalanine in it, right? It's not just to go off one diet. So you can be careful. It's a lifetime, it's a mutation you're born with. And luckily, because if you continue using it, as you know, it could lead to potential a significant mental retardation and so forth and so on. So consequently, these people with this particular mutation are always going to have an impact that they have to watch and eat and read everything before they can consume it. Other example of environmental influence on the expression of a gene are those that initiate cancer development. Radon is a very good example of that. That was discovered not too long ago, and now all of a sudden, in every real estate, when you go and buy a house, they have a radon testing for you, right? Because that became, I think it was their mine, maybe the people, they were in mines that they decided that it was discovered that they were inhaling a lot of radon and led to lung cancer. So radon is a second cause of lung cancer. So anyway, can we test gene expression? Quite frankly, yes and no. We can test them. We do it at our laboratory. That's falls under transcriptome testing. But we do it on a biopsy of kidney samples that come to our laboratory in order for a transplanted kidney to see if this kidney is going to be rejected by the body or not. But can I test your gene if you have predisposition to a liver disease? Not unless I have a piece of your liver, right? So it's again because it's temporal and it's the off and on-ness of it's just you have to get to the source. So if I just get a blood sample or a buccal swab sample from you, it's not going to necessarily cut that. But the off and on, by the way, is measured by whether or not we have the mRNA transcripts in the given cell or not. So, again, as I said, there is an interindividuality between cells and the timing, but also the actual tissue type is going to be impaired. So in reality, for the purpose of you and I in this room, we're not really going to be measuring the gene expression and epigenomic, not as easily as people claim it to be. So on a broader scale, whole genome sequencing, exome sequencing, and other testing are things that are also thrown in, and now we're getting out of the chromosomal structure into the sequences. So if this is a book of genes, we probably have out of the 3.5 billion DNA code that have been discovered, if you were to put them all in lines, you probably will have 127 volumes of book, 1,000 pages each. So, and if you look at it, as Dr. Corey mentioned, the entire genome may be 127 volumes, but your exome is going to be just about 2% of it, or under 5%, as you mentioned earlier. And again, I won't go over this, about anywhere between 20 to 30,000 genes are already known, nucleotides are already explained. They are A, G, and T, and C that are going to be pairing up. So I'm going to go past that. Those determines the codes. So we get to the holy grail of the genome. What is the goal for whole genome sequencing is to decrease the uncertainty in medical decision making and improve the clinical outcome. So the whole genome is irrelevant into anything but determining a clinical diagnosis, and the clinical utilization for all practical purposes for the present time, before we get to the Gattaca moments, is to know a preconception, carrier screening, the fetal aneuploidy, the genotyping in order to target and to treat cancer, and or a genetic predisposition, this screening when you can't really dictate by a normal screening. So examples of the preconception is that evolved testing that you and I used to do for Tay-Sachs disease in Jewish population. Nobody was confused about that. As a physician, you ordered that before people got married, before they had a child. They wanted to see, because it's so predominant in Jewish population, as a clinician, you ordered that test, right? Well, nowadays, you do it in a whole genome, because not only, well, this is one condition, Nowadays, many conditions are known that are going to be genotypically important. So why do we even test it? Because if you and your lover both have that gene, that recessive gene, you can actually go down the path of a pre-implantation genetic diagnosis, when you can choose an embryo that is going to be not having this particular problem, right? So your offspring will not be genetically implicated. This is my first grandchild picture, just so you know. This is my beautiful daughter, and yes, she did have to do the non-invasive, not because just simply because this is something that you want to do. In the old days, they do amniocentesis. Now they do whole genome sequencing in a non-invasive manner. When they do take a blood from mom, as opposed to digging for amniotic fluid, the mom's blood contains some of the fetal DNA. Remember that that's mixed with mom's DNA, so it's a very difficult testing to perform, and that usually the fetal portion comes the apoptotic placental cells. It's going to be about 10% of total DNA in maternal plasma, and of course, usually about 7 weeks of gestation is when we can actually separate or detect this, and then of course, keep in mind that right postpartum, 2 hours after postpartum is gone. So consequently, you can't expect that to linger on for the next pregnancy. So each pregnancy, you can do this testing, the whole genome sequencing on your unborn child instead of doing the invasive amniotic fluid testing. I'm not going to go through the technology of it or bore you, but needless to say, all I will tell you is that it's the cell-free DNA. You segregate maternal DNA from the fetal DNA, and you run that on next-generation sequencing, and then you start doing a counting of what belongs to each chromosome. Edwards syndrome, chromosome number 18 or 13, and chromosome number 21, and some others are being detected by this, and many others as you wish, but often the most utilized ones are for those top 3, chromosome 13, 18, and 21. You can also use the whole genome sequencing for neoplastic reason, either determining the cancer or predominantly treating the cancer. This is an excellent example when there is at the time of presentation of this patient, the DNA from the primary tumor showed a baseline mutation. It was APC. Then they put, the KRAS was wild type. They put the patient on EGFR. The burden of tumor got less, but then they continuously monitored the patient. The DNA showed the KRAS mutation and the NRAS mutation. Then, of course, the type of therapy changed by that. So you can appreciate that it's imperative technology, and that's done by whole genome sequencing. So unless if you have a patient that you're doing a therapeutic approach of bringing their burden of their tumor down, whole genome sequence, or if you have a pregnant person, whole genome sequencing is really rubbish. The genetic predisposition, a broad range of usually Mendelian variants that you don't know what they might be. There was a consortium of personal genome sequencing outcomes. Despite the fact that a lot of these whole genome sequencing is done, that we don't really know what we are targeting, and we're just testing them, with the hope of finding some of the known Mendelian syndromes. This particular study showed that 21 out of 100 participants actually were asymptomatic and yet showed various different Mendelian genetic mutations. So, yeah, it could be good, but are we there? Not really, because we don't even know what they mean, other than the fact that 21% of the population still has something that we are totally unaware of. There are many challenges. There are a lot of various rare variants and that we've never heard of. We don't know what to do with them. And of course, the expert definition of these variants differ from one group to another. So challenges are many. So okay, let's say that we don't care about the whole genome, let's just target only 2% of the genome, exomes, only the exons, as Dr. Corey mentioned. So that's the 2% of the gene that's known as exome sequencing. Well, that's probably more or less defined, and it's a little bit more controlled. But then again, folks, when you use it is when you're looking for a specific reason that is a germline mutation, a mutation that has been passed to you from your mom or dad. Not necessarily any somatic mutation that the environment or some disease or food can bring in us. Generally speaking, you're going to be testing the patient, the proband, and mom and dad. Generally speaking, it's useful, diagnostically speaking, to identify the patient, if the genetic disorder is existing in them or not, to better understand the history of that disease, to be able to target the management of the disease, to predict if there is a family member or a sibling who could be at risk, and to predict the recurrence of this risk, and whether or not you want to have a child, or do a genetic screening before you have a child. So those are all indications of exome sequencing, that you have the whole genome, the whole exome sequence for patients that are suspected of a genetic disorder, but they remain without any particular phenotype. The patients who have enormous negative or inconclusive genetic testing done, and nothing is known about them, but they're still suffering from something. Patients that have a phenotype within a family history, but they have not been diagnosed yet. Patients who have a phenotype that has been going around, but they may have one specific disorder being expressed. Patients with suspected genetic disorder with numerous underlying genetic causes that you can't simply test them for 1 million different tests, so you might as well just slap the entire test at them. And the patients with suspected genetic disorder, which specific molecular genetic testing is not capable of identifying. So those are all good indications, but again, as you can appreciate, the interpretation of that test remains within the family history. The very first case of whole genome sequencing was a baby, a 15-month baby with all sort of various, from perianal abscesses to very distinct ailment that they couldn't diagnose. And when they discovered that they did all sort of genetic testing and they couldn't find anything, they finally did an exome sequencing, and surely they found an X-linked inhibitor of apoptotic of the cell and causing all the problem. The child, of course, because of the nature of this was done by a transplant, a bone marrow transplant to go through the full wellness of this child. So this was the first clinical application of whole exome sequencing. So getting out of that to the GWAS, the genome-wide association studies, is when they've got a lot of people tested, hundreds of thousands over time, and they classified them to different disease, and they looked at the genetic permutations at the SNP level, and then they were able to put them in different buckets of association of those diseases. This is an example of fat markers. There are many of them, as you can appreciate, based on the BMI, based on the obesity, the body fat percent, etc. So this is the foundation of GWAS and various diseases that have been recognized, such as, for instance, the APOE, the E4 variant with association with Alzheimer's disease. There are limitations in genetic, the GWAS limitations, the disease risk assessment could be potentially utility and validity of it may be questionable. The risk assessment methods, it was earlier discussed. What is a risk assessment today may not be tomorrow, depending on the population and additional information that we find. The SNPs are 99.9% of the basis of basically 0.1% of what makes us. Dr. Corey has already gone through this, so I just so this is an example of when you look at AGTCs and normal, but there is this one abnormal. So like a needle in a haystack. They could be found in either the coding areas in your exome or non-coding the rest of your genes. Their will that be significant in the diagnostic will be in finding the predispositions, the health discovery, the drug discovery, and response, and then of course finding the patterns of migrations of humans. Other examples, there is a deletion, there is a large deletion in muscular dystrophy, there is insertion. This is something that the Huntington disease in chromosome number 4, which could be consequences are significant. The multiple mutations that can be seen that may be seen in a variety of disease and so forth and so on. So we have all got a variety of consumer direct-to-consumer testing. It could be done for the risk assessment, maybe ancestral, maybe kinship, maybe lifestyle. For those that are used for health and disease risk assessment is the chance of developing a disease that could predict. Basically, again, we have already discussed there are beyond just one SNP involved in that, but at least you know that if you have the SNP, you can change your lifestyle. Ancestry, of course, we know who is our parent or sibs, and the lifestyle changes. From the metabolic activity of our bodies, through specific traits can be assessed by some of these. The benefits are less expensive. They promote awareness of genetic disease. They can help you proactively to change your lifestyle. They don't require necessarily a health provider interpretation, as long as the laboratory puts the interpretation and provides a professional to assist you. The risks are many. There may be, again, not something you may be looking for, but not necessarily be detected by that SNP. May not be a definitive. It doesn't, still to this day, doesn't have enough oversight and regulation. There are a lot of companies born who just throw every garbage, unfortunately, out. So you really have to be careful with that. You definitely want to use a laboratory that is licensed and accredited, has experience and expertise in genetics, does provide a professional person to give you the consultation that's needed, and uses validation, test and sound testing. I won't go through this very much, but please keep in mind an accreditation is something that can be achieved, but it's an accomplishment to maintain that, because you have to use very proper personnel. You have to use a very controlled process in order to have the right validated equipment, the validated vendor, the validated documentation and record, the validated assessment of every given gene that you're going to be putting on your test menu. And technically, this is what we use, and this is to be a scientifically sound. The SNP has to be investigated by peer-reviewed publication. Just to throw anything out there is not appropriate. It has to be affiliated and associated with a gene that is going to be relevant to the given disease, and the minor allele must be present at least in greater than 10%. Otherwise, you have a ton of negative results. Cost. It is determined by how much your vendor is offering you, whether those products are coming with kit or not, shipping or not, a genetic expert or not, and so forth. But in conclusion, I'll leave this for you. Although the interpretation of genetic information in clinical encounters is still ambiguous, the medical decision making in the setting of an incomplete understanding of human biology, folks, has been a part of caring for patients for thousands of years. You as a clinician know this better than anything. That it's not that you're shooting in the dark, but you don't know the entirety of the human being. And like personal computers and cell phones, we can't just say, well, this is too complex, I'm going to throw that. There's no way going back. So the question for all of us to ponder, does all of this information that is thrown at us really make our life easier and make the uncertainties improve, or does that leave us in more complexity of treating our patients?